And the reason is that we have to consider similarities that are present on one side between the so-called classical mechanics or analytical mechanics and quantum mechanics. And later on, we shall consider also similarities that exist between quantum mechanics on one side and matrix algebra on the other side. Likely some of the issues that I'm going to introduce today are already known to you, so I will not devote too long a time to them, okay? I'm recalling that analytical mechanics has different forms. The very well-known form is, of course, Newton's law, in which the acceleration of a body is proportional to the force. We are considering only the non-relativistic case, okay? So the mass of the particle is always a given constant. And the force acting on the particle in the more general case is a function that depends on the position of the particle, on the velocity of the particle, and explicitly on time. This is the most general form of the force. Now, if you take Newton's law that is expressed by equation 1.1, let me make it larger if possible. Okay. And you split it into the components, you obtain something like equation 1.2. That is, the second derivative with respect to time of each component is equal to some function that depends on the components of position, velocity, and time, okay? The second formulation of mechanics that we are now considering is due to Lagrange, is the so-called Lagrange form that is based on the Lagrangian equations that are 1.3. And in general, they are written in a form in which the explicit expression of the force is not visible, okay? We introduce a Lagrangian function, L, that depends on position, velocity, and explicitly on time. And we state that equation 1.3 is equivalent to Newton's law, simply. What is the form of equation 1.3? Is that on the right-hand side, we have the derivative of the Lagrangian with respect to the generic coordinate xi. On the left, we have the derivative of the Lagrangian with respect to the component of the velocity with the same index, x dot I, and then after calculating this derivative, we take the total derivative of the result with respect to time, okay? So we claim that we are able to find a function L such that 1.3 becomes identical to 1.2. This is not always possible. That means that if I prescribe a fancy form of the force, it is not necessarily true that I'm able to find a Lagrangian, okay? But there is a very special situation that is also very important, and this is the situation in which the forces are conservative, okay? So they can be derived from a potential energy that depends only on position, okay? In that case, it is always possible to find the Lagrangian, and the expression of the Lagrangian is quite easy. In that case, if the forces depend only on position and are derivable as for each component as minus the derivative of the potential energy with respect to the component of position, in that case, the Lagrangian is simply equal to the difference between the kinetic energy and the potential energy. We imply that we are using the Cartesian coordinates. So obviously the kinetic energy is 1/2 m, the square of velocity, that expressed in using the components is x1 dot squared plus etc., as you see in equation 1.5, okay? I anticipate that I will post these pages in the website, okay? So it is not necessary that you copy word by word the equations. This is a very important case, and we shall confine our consideration only to the conservative case. Why should we bother using the Lagrangian? We may say we already have Newton's law, okay? Well, there are some advantages. One advantage is that by looking at some symmetries of the Lagrangian, for instance, you may have that the Lagrangian is invariant if you shift the origin of the coordinates, okay? So if the Lagrangian is invariant with respect to the position of the origin, then the total momentum, the momentum of the particle or the total momentum of the system is conserved. Then if you find that there is another symmetry, that is the Lagrangian is invariant after rotation of the reference around the origin, then you find that the angular momentum is conserved. Also, if you find that if the Lagrangian is invariant upon mirroring time, that is, you replace t with minus t, okay? Then the total energy is conserved, etc., etc. So you may simply find interesting properties of the particle or system of particles simply by looking at the form of the Lagrangian. Obviously, if you consider the conservative case, you find immediately that since the Lagrangian is equal to t minus v, and v does not depend on the components of velocity, the derivative of the Lagrangian with respect to x dot is like the derivative of the kinetic energy with respect to x dot, and that makes the component of momentum m times velocity. So that if you take the total derivative, you find m times the second derivative of position, that is acceleration. And similarly, when you take the derivative with respect to position, you find that the kinetic energy does not depend on position, so you find that it is just equal to minus the derivative of the potential energy with respect to position, that is the component of the force. So you recover immediately Newton's law just by applying the expression of the Lagrange. An important definition is this. If you go back to the original Lagrange equation, you see that on the left we have the total derivative with respect to time of a quantity that is the derivative of the Lagrangian with respect to the component of velocity. This is a quantity that is very important, and it is also called momentum, pi, conjugate to the component of coordinate of the same index I. Okay, so this is momentum. Momentum is equal to the product mass times velocity only when we have the conservative case and in Cartesian coordinates. Okay, but this definition of momentum is more general because you may have other situations in which the force is non-conservative, like for instance the electromagnetic force. So in that case, the momentum turns out to be different from the product m times velocity. Okay, pi and xi, that is the momentum and the coordinate with the same index, are called conjugate or canonically conjugate pairs. Okay, and if you have one particle, the particle has 3 degrees of freedom, x1, x2, and x3. So there are 6 canonically conjugate coordinates, 3 pairs. Okay. And the set of these coordinates is also called the state of the particle. So in classical mechanics, the state of a particle is the set of positions and momenta of the particles. If you have a system, you have a larger set that is made of the complete set of the position coordinate and momentum coordinates of all particles. Okay? Remember that when we call a set of particles, we can call it system only if the particles are interacting. Okay? If we have n particles, but these n particles are not interacting, they are not one system, they are n separate systems. So we can simply treat one particle at a time without considering the rest. Okay? So when we talk about a system, we imply interaction among the particles that make the system. Okay? So we can easily generalize the concept by simply stating if you have a system instead of having a single particle, then you have a number of degrees of freedom that is 3 times the number of particles, so 3n. We assume that there are no constraints, okay, because you remember that constraints, each constraint decreases the number of degrees of freedom. So we assume that there are no constraints. A possible example of a constraint is that when you have 2 particles that are rigidly connected with a bar, okay, so the distance between the two, the bar can rotate, but the distance between the 2 particles is kept fixed by the bar. So we have 1 degree of freedom less, okay, because the mutual distance between the particle cannot change. We assume that we do not have any constraints. So there are 3n degrees of freedom. We call this number small s. So small s is the total number of degrees of freedom of the particle. And then we simply extend the concept by considering that the force, the ith component of the force acting on the degrees of freedom of index I depends on the positions and velocities of all particles and time. That means that all particles act on every other particle of the system. And similarly, the Lagrangian turns out to be a function of all positions and all velocities and time. Just the same. The Lagrangian equations do not change when we go from one single particle to a system of particles. Simply the number of equations becomes equal to the number of degrees of freedom. Okay? So we have the same expressions for a single system of particles as for a single particle. Another advantage of the Lagrangian formulation is this. It is not necessarily true that the Cartesian coordinates are always the best choice. There are situations, if you think, for instance, of a problem in which you have a central force, like that of a satellite and a planet, okay? In that case, when you have a central force, and that means that the force is directed along the line that connects the satellite with the planet, it is more convenient to use spherical coordinates instead of Cartesian coordinates. That means that one may more profitably describe the position of the satellite by considering the distance from the planet and two angles. Okay? The usefulness of the Lagrangian description is that when we change the coordinate system, the form of the Lagrangian equation does not change. Okay? So when we go from the Cartesian coordinates to any other set of coordinates, so let's call it generalized coordinates, okay? The generalized coordinates are just other coordinates that we used to call with the symbol Q that are uniquely connected with the original Cartesian coordinates. That means that we have at our disposal a set of functions like 114 that define each generalized coordinate Qi in terms of the Cartesian coordinates x1, xs, and possibly t. The dependence on t may come if the new reference is moving with respect to the old reference, okay? Obviously, we assume that the relations that connect the old coordinates to the new coordinates are invertible, so that we are able to extract each Cartesian component from the set of the Q coordinates. You are very well accustomed, if you have been using it in some problems, the spherical coordinates, you know how to go to and fro the Cartesian to the spherical coordinates. After defining the new set of coordinates, the calculation of the derivatives is purely mechanical. You take the derivative of 114 with respect to time, and you end up in calculating the q dot. They are called the generalized velocities that in general are a function of all the Cartesian coordinates and all the velocities in the Cartesian coordinates, okay? Q dot is called the generalized velocity. It happens that the new coordinates Q are not necessarily lengths. They do not necessarily have the units of a length, okay? Think of the spherical coordinates in which you have one distance, that is the distance between the satellite and the planet, and that is a length, but then you have two angles. So for that reason, the generalized velocities, are not necessarily a distance over a time, okay? The time in the denominator is there, but the numerator is not necessarily a distance. Then you may recalculate the Lagrange equations in the new coordinates, and the very good news is that their form is the same as in the old coordinates. You can see it is equation 1.18. The Lagrangian equations are invariant upon a change in the coordinate system. So we can use the same form no matter what the coordinate system is. This is very important because it is very useful. We don't have to worry about this change of coordinates. Now, if you look at the definition of the Lagrangian of the conservative case, that is the kinetic minus the potential energy, you find immediately that the Lagrangian has the units of an energy, okay, because it is homogeneous with the energy, okay. Now, if you look at the definition of the generalized momentum, okay, the momentum P in the new coordinates is of course defined as the derivative of the Lagrangian with respect to the generalized velocity with the same index, okay? So the observation is that when we go from the Cartesian coordinates x to the generalized coordinates q, we change the symbol of the coordinates. Instead, when we consider momentum, we do not change the symbol. We still call P with the symbol P the momentum in the new set of coordinates. So the generalized momentum P given by 120 is the derivative of the Lagrangian with respect to the generalized coordinate, okay? Of course, since the units of the generalized coordinate depend on what system of coordinates you're using, okay? So you don't know a priori. If you don't specify exactly what system of coordinates you're using, you don't know the units of Q, okay? So as a consequence, you don't know the units of P in the new coordinates, okay? But you can immediately find the units of the product P by Q, okay? Because you can see it here. If you bring this differential to the left, you have P times the differential of Q dot, okay? So this quantity must have the units of an energy, because on the right we have an energy, delta L, okay? So PQ divided by a time, because you have Q dot, is equal to an energy. As a consequence, the units of Q, you can see this in equation 122, the units of Q times the units of P in any coordinate system, are equal to the units of the Lagrangian times the units of time. The Lagrangian is an energy. So the product LT has the units energy multiplied by a time. This is a unit that is also called action. It is written here. So energy multiplied by time is action. And you may remember that the Planck constant has the same units, okay? So there is a connection with this. The Planck constant has the units of an action, okay? This is not enough. The formulation of the analytical mechanics using the Lagrangian function is not the only possible, besides that of Newton, based on the Newton law, is not the only possible formulation. There is another one that is very much used, that is the Hamiltonian formulation of mechanics. The Hamiltonian formulation is derived formally in a very straightforward way from the Lagrangian, because you remember at some point we define the generalized momentum, Pi. Pi is the derivative of a function, and you see this function, if you look at 119, this function depends on all coordinates, all velocities, and time. So the same is for Pi, because it is the derivative of such a function. So we know that by construction, each component of the generalized momentum depends on all generalized coordinates q, generalized velocities q dot, and time. So in general, we succeed in inverting these relations. We can extract from these relations that are as many as the number of degrees of freedom of the problem. We can invert by extracting the q dots as a function of all the q and pi's and p's, and time. Okay. Given that, what we do is the following. We formally define a function h that is the sum over the degrees of freedom of the individual products of each momentum Pi times the corresponding generalized velocity q dot. And after we calculate this sum, we subtract the Lagrangian. So we have a messy expression in which we have a mixture of q, q dot, and p coordinates, okay? But after doing that, we exploit the equations of the form 124, okay? And we replace each q dot here and also inside the Lagrangian with the expression that depends only on the position, momenta, and time. So in conclusion, after these calculations that are purely formal, okay, we end up with a function that we call the Hamiltonian function of the system of particles. And this Hamiltonian function happens to depend on all coordinates, all momenta, and possibly on time. Okay? So this is a purely formal analysis. What is the usefulness of the Hamiltonian function is that we can formulate analytical mechanics in terms of the Hamiltonian function. And actually, one can demonstrate that if you take the derivative with respect to the momentum, any of momenta of the Hamiltonian function, you obtain q dot, the conjugate velocity of the same index. And if you instead take the derivative of the Hamiltonian function with respect to the generalized coordinates with the minus, you obtain the time derivative of momentum p dot, and of course this is, as you remember, the force acting on the ith degree of freedom. In conclusion, one can demonstrate that equations 127, that are called the Hamilton equations, are fully equivalent to the Lagrange equations. And you remember, in turn, the Lagrange equations are fully equivalent to Newton's law. So Newton's law, Lagrange formalism, and Hamiltonian formalisms are three equivalent methods to describe analytical mechanics. Why should we bother with the Hamiltonian formalism? And the reason is this, that it is very general. For instance, it is possible to extend this formalism to cases in which we don't have particles, like we can extend the formalism of the Hamiltonian function to the field. It is possible to write down the Hamiltonian function of the electromagnetic field, for instance. And you remember that we have been talking about Hamiltonian operator in quantum mechanics. The Hamiltonian operator of quantum mechanics is the counterpart of the Hamiltonian function of classical mechanics. So the Hamiltonian function is a very general problem. You can also see that the Hamiltonian equations 127 are first order equations because we have q dot and p dot. So we have only the first derivatives, okay? How many equations do we have? Well, we have each pair of equations is repeated s times because we have one equation for each degree of freedom of the system. So you remember that the first order equations need one initial condition. So the total number of initial conditions for equations 127 is 2s, because we have two equations for each one of the s degrees of freedom of the problem. Okay? In the Lagrangian formulation, we have one equation for each degree of freedom, like one equation like 118, okay? But this equation is of the second order with respect to time because we have q dot, so we have the first derivative here, but then we take the derivative again, so we have the second derivative of the q's, okay? So also in this case, we have s equations, and for each equation we have, the equation is of the second order, so we need two initial conditions, one for the function and one for the derivative. So the total stays the same. The initial conditions in any case are 2s, okay? You remember we derive the Hamiltonian function with the manipulation that involves the Lagrangian function. That implies that in order to calculate the Hamiltonian function, then the Lagrangian function must exist, okay? And you remember that not in all cases the Lagrangian function does exist. But it does exist in a very special case, and this special case is that of the conservative system, okay? So we expect that since the Lagrangian function exists for the conservative system, then also the Hamiltonian function will exist in a conservative system. The answer is in the positive, of course, and you remember very well that for a conservative system, the Hamiltonian function is equal to the sum of the kinetic and potential energies. That is the total energy of the system. And the system is, by hypothesis, conservative. That is, the potential energy V depends only on the coordinates, and the forces are derivable as minus the derivatives of the potential energy with respect to positions, okay? So in this case, the Hamiltonian function is equal to the total energy, and this total energy is a constant with respect to time, so it is conserved in time, which may look odd because V contains the positions of the particle, and obviously they change with time. So V changes with time intrinsically or implicitly better, because although there is no explicit dependence on time, all the positions of the coordinates depend on time. But also the kinetic energy has the velocities in it, and the velocities do depend on time. So individually, T and V do depend on time, but their sum is such that it is a constant. Okay, so they cooperate in order to provide a constant total energy of the system. Of course, the kinetic energy is always in Cartesian coordinates the sum of the individual kinetic energies. Okay. If you consider the Hamiltonian equations in the conservative system, you immediately find with an easy calculation that you have back Newton's law, because Q dot is the derivative of H with respect to P, but only the kinetic energy depends on P. So it is equal to the component in the Cartesian coordinates is equal to the component of the velocity. And there is a mass missing here. No, there is no, it's correct, sorry. Then the P dot is minus the derivative of H with respect to Q, only the potential energy depends on Q. So this is a misprint, okay? The Pi in the denominator should be Qi. This is a misprint, okay? And this is obviously the force acting on the particle. P dot in Cartesian coordinates and for conservative forces is equal to the mass times the velocity, okay? Sorry, times the second derivative of position with respect to time, so the acceleration. So this is again Newton's law, okay? We already mentioned the existence of constants of motion, and in particular, if you have a system that is subjected to conservative forces, the total energy is a constant of motion. This can be easily demonstrated, okay? Because take a single particle for simplicity, okay? If you consider the force acting on the particle, okay? And then you consider a small amount of time, dt, okay? In that small amount of time, the particle will be displaced by some amount of space dr that is equal to the velocity times dt, okay? So you remember that if you multiply scalarly the force by the displacement, you find the work. If this work is positive, then it is the force that is acting that is increasing the energy of the particle. So the particle is absorbing energy from the force. If the product is negative, then it is the particle that is releasing energy to the force field, okay? In any case, when you replace the displacement with u dt, and then you remember that F is the mass times the acceleration, that is mu dot, okay? And then you go to the next line, you find immediately that this expression can be written as the derivative of u dot u divided by 2. So you eliminate the differential of the time. You are left with this. Then you replace the velocity with the product. Sorry, the velocity is equal to p divided by m. So you obtain this, okay? So the elementary work exerted from the force into the particle or vice versa is equal to the differential to the variation of p squared over 2m. That is, of course, the variation of the kinetic energy. But in the conservative case, the force is equal to minus gradient of v. So the scalar product of minus gradient of v times the displacement is, of course, minus the variation of v. So you see that the same starting expression, that is F dot dr, here it provides the variation of the kinetic energy. And there it provides minus the variation of the potential energy. So these two quantities must be equal. That is, the sum of them is 0. So the variation of the total is 0. And the total is, as you remember, the total energy. Okay? Before we start the intermission, I just want to make a few more comments about this. You remember that if a system has S degrees of freedom, you need a number of initial conditions that is equal to 2 times S. Okay, because you have a set of equations. It doesn't really matter whether you are using the Lagrangian, the Newton, or the Hamiltonian formulation. In all cases, you have a set of differential equations with respect to time that do require a total number of initial conditions that is equal to 2s. Okay. Of course, you may think that these numbers are the values of the positions and velocities at t equal to 0. Or if you are using the Hamiltonian formulation, they are the values of the generalized coordinates q and of the generalized momenta p at time e equal to 0. Okay, so the issue is that you always have 2s constants, and you may consider them as constants of motion. Okay, and you may also combine them in many different possible ways in order to find other constants of motion. So the total energy of the conservative system is a constant of motion that you may, if you want to, express in terms of the initial positions and momenta of the system. So in terms of the initial values of the coordinates and momenta. So this constant of motion, that is the total energy, is not an additional constant of motion. Okay, you don't have 2s plus 1 constants of motion just because you found that the energy is conserved. It is simply possible to express the energy in terms of the initial conditions of the motion. So the actual number of constants is always equal to 2s. Okay? Now we stop and we shall continue in 10 minutes. Okay, you should be able to see a page with paragraph 1.5. And let's proceed in the description of the formalism of mechanics by considering the coordinates and momenta. So we are using the Hamiltonian formalism, okay? And let's consider a vector in which we plug one after the other all coordinates q followed by all momenta p. So if we have a system of with s degrees of freedom, so we have 2s canonical variables q and p, we have a big vector defined by 137 and we call it C, okay? Of course, this vector depends on time because each component of position and momentum depends on time. So this vector depending on time provides the full information about the state of the system at time t, okay? Now we can think of a space in which we have two s coordinate axes. S of them are related to the components of Q, and the other s coordinate axes are related to the components of P, okay? So this is a space with two s dimensions, okay? In this space, vector C represents a point. This vector joins the origin of the space to some point defined by the coordinates q and p, okay? So in this space, a single point represents globally the state of the system. The position of this point in the space moves with respect to time because as time evolves, the coordinates and momenta change. So the representative point C moves in time and describes a trajectory. So let's give names to these concepts. The space of C is called the phase space, or also Gibbs space, or also gamma space. Gamma stands for gas, because the typical example to which these concepts apply is that of a gas. We have that each molecule of the gas has a position and a momentum, so the total number of coordinates will be given by the total number of positions and momenta of the gas, okay? Why is this useful? Because now we can remember that in the Hamiltonian formulation of mechanics, Q dot here is equal to the derivative of the Hamiltonian function with respect to P. And P dot is equal to minus the derivative of the Hamiltonian with respect to Q. So if we consider this big vector C and take the derivative of each Q and each P. Globally, we have the derivative of C. We call it C dot, okay? And then we can replace to each Q dot the derivative of the Hamiltonian with respect to the corresponding P, and similarly for the second part of the vector. So if we take C dot, that formally is a vector of components Q1 dot, Q2, etc., down to PS dot. And then we replace the Hamiltonian equations. We find this expression for C dot, okay? Obviously, remember the Hamiltonian function depends on all Q's, all P's, and possibly on time. So this quantity C dot is a function, is a vector function of all coordinates, all momenta, and possibly time, okay? So by this observation, we may think of calculating the divergence of this vector, okay? You remember, by definition, the divergence of a vector is equal to the derivative of the first component of the vector with respect to the first coordinate, plus the derivative of the second component of the vector with respect to the second coordinate, and so and so and so. Okay, so we have an expression of this form in which from 1 to S, the numerator of the derivative is one of the Q dots, because the first half of this vector is filled with the Q dots. And the denominator is Q, because the first coordinates are Q1, Q2, etc., etc. The second half of this expression here is made of fractions in which the numerator is one of the P's, sorry, the P dots, and the denominator is one of the P's, okay? So we can put all these things together and find that the first half is the derivative of Q dot over with respect to Q, added up from 1 to S, plus the second part of the divergence is the derivative of the P dot with respect to the corresponding P. But at this point, we remember that Q dot is the derivative of the Hamiltonian with respect to P. So the first term in this parenthesis is also the second derivative of the Hamiltonian with respect to Q that was already there, and with respect to P, because Q dot has the derivative with respect to P. Similarly, P dot is minus the derivative of the Hamiltonian with respect to Q. So you can see that these two quantities are equal, but they have the opposite sign. That means that they cancel each other. So the divergence of the vector C dot, that is globally a vector made of the Q dot and the P dot, the divergence is equal to 0. The symbol divergence with respect to gamma indicates that we are doing the divergence with respect to all coordinates and momenta. Okay. We have a similar expression in fluid dynamics. Okay, if you take a fluid and you want to state the condition that the fluid is incompressible, that means that if you push the fluid with any force, the volume does not change, okay? the incompressibility condition of the fluid has the same expression. Okay, so this is an important analogy. Okay, but we can go further. We can consider now the product of the C dot vector times a function that it is not specified, okay, is some function that we call sigma that depends on the coordinates c and time, okay? And then we calculate the product of this function sigma times c dot. And then we calculate again a divergence, but in this case we want to calculate the divergence of the product sigma c dot, okay? We can do it by applying one of the very well-known vector identities, okay? That is the divergence, you remember, the divergence of a scalar, that is sigma, times a vector, is equal to the product of the scalar times the divergence of the vector. You can see here sigma divergence of c dot plus the vector scalar product, the gradient of the scalar function sigma, okay? But we just a minute ago demonstrated that the divergence of c dot is 0. So in conclusion, the divergence of sigma c dot for any sigma is equal to c dot scalar product gradient of sigma, okay? This is purely formal calculation because we did not specify yet what sigma is. Sigma is any function of the generalized coordinates, and t could be the Hamiltonian, for instance. Okay, we shall see. Next, given sigma, we can also define the total derivative of sigma with respect to time. The total derivative, you remember from calculus, is equal to the partial derivative, that is the derivative of sigma with respect to the explicit dependence on t if it exists, okay, plus the sum of the product of the individual derivative of sigma with respect to each of the generalized coordinates times the derivative of the generalized coordinates with respect to time, okay? But you see immediately that this sum is nothing else than the scalar product of c dot, that is dci over dt, times the gradient of sigma, okay? So at this point, we may combine these two equations, 141 and 142, because you see that the last term, c dot scalar product gradient of sigma, is equal to the divergence of sigma c dot. So by combining these two informations, we find that for any function sigma that depends only on the generalized coordinates and time, the total derivative is equal to the partial derivative with respect to the explicit dependence on time plus the divergence of sigma times c dot. C dot is the vector made of the q dot and p dot, okay? There is another possible form of the scalar product that goes under the name of Poisson parentheses. So we shall now introduce the Poisson parentheses of two functions, generic functions that we call A and B, that depend on the conjugate variables and time. Okay, so the Poisson parenthesis is written by this symbol, is the brace A comma B brace. This is the Poisson parenthesis. Is by definition equal to the sum over the dimensions of these vectors, of these coordinates, of dA with respect to Q times dB with respect to P minus dA over dP, dB over dQ. So you see that in the denominators we have swapped the P and the Q coordinates. Okay? So why should we bother about the Poisson parentheses? Okay? Well, the Poisson parentheses have some link with the commutator of operators, we shall see. Okay? So we shall find a formalism in quantum mechanics in which we have quantities that are reminiscent of the Poisson parentheses of the analytical mechanics. Okay? Now we manipulate. You remember we have this relation here that C dot gradient of sigma equal to the divergence. We can express C dot gradient of sigma because if we split the first half of the vector, the first part of C dot is Q dot. And the first part of the gradient of sigma is made of the derivatives with respect to the Q's. So we have this. And then we have plus P dot derivative of sigma. This is the second half of the scalar product. You spot immediately that we have the derivative of the Hamiltonian here with respect to P, and here we have the minus derivative of the Hamiltonian with respect to Q. Okay, so when we replace this, we find a Poisson parenthesis of sigma with the Hamiltonian. There it is. Okay, so we have found that C dot gradient of sigma that is also equal to the divergence of sigma C dot is the Poisson parenthesis of sigma with the Hamiltonian. So we can replace it here. We can give another form to equation 143. So this is another possible expression that we shall find almost identical in a quantum mechanical situation. The total derivative of any function that depends only on the coordinates, okay, made with respect to t is equal to the partial derivative plus the Poisson parenthesis of sigma h. Sigma is any function. So we may think of an example in which sigma is equal to the Hamiltonian, okay? But if you take sigma equal to the Hamiltonian, obviously the Poisson parenthesis of a function with itself is equal to 0 because all terms cancel each other, okay? That shows formally that the total derivative of the Hamiltonian function in all cases, because this is a fully general analysis, is always identical to the partial derivative of the Hamiltonian with respect to time. That is, the derivative with respect to time is non-zero only if the Hamiltonian depends explicitly on time. Okay? If the Hamiltonian does not depend explicitly on time, then the partial derivative in equation 147 is 0. That means that also the total derivative is 0. So if there is no explicit dependence of the Hamiltonian on time, then the Hamiltonian in itself is a constant of motion. We are not finished with the different formulations of the analytical mechanics, because there is another possible formulation that is called the Hamilton-Jacobi equation. Okay, it is just another possible form of analytical mechanics. Okay, this new formulation requires the introduction of a function that we call S, capital S. And this function is called the Hamilton principal function. Okay, so the unknown of the problem in the new formulation is this new function. Okay. Again, we derive this new function with the purely formal manipulation. You remember how we define the Hamiltonian. Okay, the Hamiltonian function is equal to the sum of the p times the q dot minus the Lagrangian. Okay, so we may put the Hamiltonian to the right and the Lagrangian to the left. Okay, and the same expression that is used to define the Hamiltonian yields this relation. That is, the Lagrangian is equal to a sum made of the products of the p times the q dot minus the Hamiltonian function. Okay. Now we formally introduce the new function S, the Hamilton principal function, as a function such that its total derivative with respect to time is the Lagrangian. So we simply state that there is some function S such that ds over dt is equal to L. Then we replace ds over dt here, and then we multiply both sides by dt. Okay, what do we obtain? We obtain that ds after multiplication by dt, ds is equal to the sum of pi q dot dt minus h dt. Obviously, q dot dt is dq, because q dot is the total derivative of q with respect to t. So q dot dt is dq, okay? So if you look carefully, equation 148 looks like a total differential. The total differential of S is equal to a sum of differentials times some factors, some coefficients, okay? So you may think that if you consider S as a function of the generalized coordinates Q, okay, you may think that if the S is a differential, you may think that pi turns out to be the derivative of S with respect to Q. Because if you take the differential of a function that depends on the Q, you must take the derivative of S with respect to Q, and then you multiply by dQ to obtain the differential. This last term here is minus the derivative of S with respect to t, because if S depends explicitly on time, then in the differential you also have the derivative of S with respect to time times dt, and then this derivative you call it minus h. Okay? So by the simply formal manipulation, we have introduced a new function, and this function S depends on the generalized coordinate, okay, and on the Hamiltonian. Obviously, the Hamiltonian also depends on the coordinates q and momenta p, okay, but since in this formulation the momenta are the derivatives of S with respect to Q, we must replace formally inside the Hamiltonian. To each pi, we must replace ds over dq, okay? So we simply manipulate the Hamiltonian function formally by replacing each component of the generalized momentum with the derivative with respect to q of the Hamilton principal function. For this reason, we change slightly the name to the Hamiltonian. We call it H sub S, just because we have made this change inside the Hamiltonian, okay? Globally, if you look, I go back for a second. If you look at this equation here, if you bring ds over dt to the left, you have ds over dt plus h equal to 0. And h becomes h sub s, okay? So we have an equation that is s, an equation in the unknown s. It is a first order differential equation, okay? In which you have the partial derivatives of s with respect to time and also with respect to the coordinates. So this is to be understood as a differential equation in the unknown s, okay? How many variables are there? Well, actually, there are s plus 1 variables, because the total number of coordinates is s, but then we have time. So this looks strange, because if you have a first order equation in which there are s plus 1 variables, then you need s plus 1 integration constants, okay? So why s plus 1? We would expect s, okay? But the issue is that if you look carefully in the equation, there is no s. There is just the derivatives of s with respect to time or with respect to the coordinates, okay? There is no explicit appearance of s in itself, okay? So if S is a solution, it is written here, then also S plus a constant is a solution. So one of the constants is irrelevant, because we have only the derivatives of S and not just S, okay? So actually, we need only S integration constants for the equation, okay? You may think that we have lost some constants, because in the Hamiltonian or Lagrangian formulation, okay, we have 2s constants, but this is not true, okay? Because when we are finished with the integration, we shall find that we have s more constants, okay, that are these constants beta, sorry, these constants beta I, okay, that are constants of motion. So the problem actually has a total number of 2s initial conditions, just the same as in the Lagrangian or the Hamiltonian formulation, okay? Why should we bother with the Hamilton-Jacobi theory? Well, if you look carefully at 151, you may see that there is a striking similarity with a Schrödinger equation depending on time. You remember the Schrödinger equation depending on time has derivative with respect to time of the wave function equal to the Hamiltonian applied onto the wave function, okay? And here we have time derivative plus Hamiltonian equal to 0, which is formally the same, okay? So in classical mechanics, this is the equation that is more resemblant to the Schrödinger equation dependent on time, okay? And this is no coincidence, okay? It's something that is deeply rooted in the theory. Now we shall introduce another concept, and the other concept is that of statistical ensemble or statistics, okay? So far, when we have considered the problems of analytical mechanics, we always implied that we possessed a set of equations of motion plus the initial conditions. So in the most general formulation, we assume that we are in the gamma space, okay? That we want to calculate the phase trajectory, that is the set of points provided by vector c that represents the state of the system at each instant of time, okay? But for that, we assume that the initial conditions of the state of the system are given, okay? However, this is not always so. It may happen also in classical mechanics that the total information about the initial state of the system is not really known. We have only partial information about the state of the system. So although we can set a number of equations that fully describe the motion, we don't know how to start with the motion. So we don't know how to precisely calculate the trajectory of the particle or the trajectory of the system in the phase space, okay? Consider a very easy example. The example of the linear harmonic oscillator in the classical case, okay? You remember that in the linear harmonic oscillator, we have a Hamiltonian function that, of course, is a constant with respect to time, so it is a constant of motion. And the Hamiltonian function is equal to the kinetic energy, that is p squared over 2m, times the potential energy, and the potential energy is a parabola with respect to the coordinate. In this case, the coordinate is indicated with q instead of x, okay? And the potential energy is m omega squared divided by 2 times q squared, okay? This is equal to the total energy that is a constant of motion. The angular frequency, as you remember very well, is the square root of the elastic constant, c, over the mass, okay? What is the trajectory in the phase space of this problem? Okay, the trajectory in the phase space is a curve in the QP space because we have only two coordinates, okay? So we have to set up a two-dimensional space. So we set up a horizontal axis for Q and a vertical axis for P, okay? And the trajectory in the phase space is made of all the pairs Q and P that fulfill equation 1.57, okay, that are such that P squared over 2m plus m omega squared divided by 2 times Q squared is equal to a given constant E, okay? Obviously, E is strictly positive because it cannot be negative because it is the sum of quantities that are non-negative, okay? And the only possibility for E to be 0 is that P and Q are both equal to 0. That is, the harmonic oscillator is in the origin and is not moving, okay? So we rule out this possibility. So E is strictly positive. If we rearrange equation 157 by defining P sub E, as you can see in equation 158, as the square root of 2m times the energy, and then we define Q sub E as 1 over omega times the square root of 2e over m, we can rearrange equation 157 in a much simpler form that is visible in equation 158. It is P squared over PE squared plus Q squared divided by QE squared equal to 1. And you remember very well that this is an ellipsis. In geometry, such an equation defines an ellipsis in which PE and QE are the half axis, okay? And you also remember that the area of the ellipsis is the product of the two half axes times pi. So it turns out to be 2 pi. If you replace the definitions of PE and QE, you obtain 2 pi energy divided by omega. And 2 pi over omega is the frequency. This is very interesting because it shows you that in the linear harmonic oscillator, the frequency or the angular frequency omega is given a priori by the constants parameters that are in the equation. So the elastic constant and the mass combine together and provide omega, and as a consequence, the frequency, okay? And the total energy is given, okay? So this curve is given as soon as you give the total energy, okay? Is immediately defined if you give the total energy and, of course, the two parameters, mass and elastic constant, okay? So the conclusion is that the linear harmonic oscillator has a representative point that corresponds to the vector C. In this case, the vector C has only two components, Q and P. And this point that identifies the state of the system simply moves along the ellipsis. Okay? It goes along the ellipsis forever. So at each instant of time, you can find Q and P of the particle, provided you know the initial condition. Okay, in order to know the position of the point in the phase space at each instant of time, you must know the initial condition. So if you have an insufficient information, if you don't possess the initial condition, even in this very simple example in which you know almost everything, okay, you don't know how to describe the evolution of the phase point along the ellipsis. You know that there is an ellipsis because the ellipsis is fully defined by the parameters, okay? But you don't know where at each instant of time the representative point of the linear harmonic oscillator is placed, okay? So you have a smaller amount of information. The only thing that you can say is that if the initial conditions are not known, you know that any point of the ellipsis is equally good to describe the system. So the ensemble of points made of all points of the ellipsis in this example is equally good for the description of the state of the particle. So you have an incomplete information of the state of the particle, okay? We may even try to decrease the amount of information because in this example, you don't know the initial condition, but you do know the total energy, okay? Assume instead that not only you don't know the initial condition, but you do not know either the total energy. But assume that you have an incomplete information about the total energy such that you simply know that the total energy is given, it stays within two limits, okay, between some lower limit E1, which is a non-negative quantity, and some other limit E2, okay? So the smaller limit E1 defines a smaller ellipsis. The larger limit E2 defines a larger ellipsis in which the smaller ellipsis is contained, okay? So the two ellipses together define a strip in the gamma space, okay? So if you have little information such that what you know is that the total energy, you know that the phenomenon is described by a linear harmonic oscillator, okay? But you know that the energy is somewhere between E1 and E2, okay? You define a strip and then you say any point of the strip is representative of the state of the particle and is good as any other point of the strip, okay? So this is the maximum information that you can achieve from this system. In this case, the ensemble is the set of points of the strip, okay? A very important observation is this. These points of the strip, or in the other example, the points along the ellipsis, okay, are not different particles that maybe interact with each other. Each point of the strip is the same particle, is a possible representative of the same particle, okay? And all these representatives are fully independent from each other. Any of them is a possible description of the same particle. So the ensemble is a set of replicas of the same particle or of the same system. And these replicas do not interact with each other. Each of them evolves according to the dynamical laws, but unfortunately we have not enough information about the initial condition about all these replicas, so we can do very little about this, okay? Or maybe we can do some statistics, okay? Some statistical treatment, that's it, okay? We cannot describe exactly the motion of the system. One other information is important. We shall consider, in all cases, conservative systems, like in the example of the linear harmonic oscillator. Okay, so we have an ensemble of particles. Okay, each of them is a replica of the same particle. Each member of this ensemble has a trajectory in the phase space. In the example of the linear harmonic oscillator, the trajectory is the ellipsis. But in no case the trajectories of two members of the ensemble may cross each other. These trajectories never cross each other for a conservative system. Okay, why is it so? It is so because if two trajectories cross each other, at the crossing point, the two members of the ensemble have the same momentum and the same position. Okay, so they have the same initial conditions. Okay, but on the other hand, since the Hamiltonian for the two is the same, because the elastic constant is the same, the mass is the same, if they also have the initial condition, and of course they have the same energy at that point because the positions and momentum are the same, okay? The evolution of the motion from that point on should be identical, because if you have two particles with the identical Hamiltonian and the identical initial conditions, then of course they follow the same trajectory, okay? So if the two trajectories cross each other, then from the time of crossing on, that is in the future, the two trajectories must be coinciding, okay? But since the equations of motion are reversible in time, that is also true if you go backwards in time. So the trajectory should be the same also in the past. But since we assumed initially that they were different, because we said at some point they crossed, so initially they should be different, this is impossible physically, okay? So for the conservative system, the trajectories of the members of the ensemble never cross each other. They are all independent and not crossing each other. We now stop for the intermission and we shall continue on the same line in about 10 minutes. Okay, let's start again. We have introduced the concept of ensemble, that is a set of many points of the phase space that are representative of the same system. And accepting the idea that we have not enough information to decide which of these points is the actual representative of our system, we must investigate the properties using some statistics. So we have to introduce some statistical concepts to continue to investigate the system. And this is easily done by considering a distribution function that we call rho. So rho is a function that is positive definite or non-negative definite. It depends on C, so that it depends on all the canonical coordinates described in the system and explicitly on time. Okay. And the property is the following, that if we take an elementary volume of the gamma space, that is a volume that we call DC, made of dq1 times dq2, etc., down to dps. Okay, so it is the elementary volume of the gamma space. In this elementary volume, at some instant of time, there will be a number of points that are the representative points of the ensemble that at that instant of time happen to stay within this elementary volume DC, okay? By definition, the function rho is such that when we multiply rho by the elementary volume, we find the number of particles inside the elementary volume. So of course, rho is a density in the phase space, and it is called also the distribution function. Okay, it tells you how the points representative of the system are distributed in the phase space. Okay. In principle, we could have infinite members of the ensemble. Okay, if we really know nothing about our system, then we have points everywhere in the phase space. Okay, so the risk is that when we go and integrate the density over the full space, we obtain an infinity. Okay, so we assume that it is not so. So that the distribution is such that when we go far away from some region of the phase space, there are no particles there. Okay, there are no, sorry, elements or representative members. So we assume that the integral of the density over the phase space is finite. Okay. That means that the total number of the elements is finite, and we call it M. Okay. Then you remember each point of the phase space is the full system under consideration. Okay. So obviously, a point of the ensemble can never disappear, can never be destroyed. or conversely, it can never be created, can never appear, okay? Each of them is just our system exists. These points do not interact with each other, they cannot be broken or destroyed or whatever. So we can easily set up a continuity equation for the density, okay? And the continuity equation is just as any other continuity equation. It is that the partial derivative of the density with respect to time plus the divergence of the density rho times the velocity must be equal to 0. This is the typical form, the general form of the continuity equation in which you don't have any destruction or creation of anything, okay? So you have a 0 at the right-hand side, okay? So the density in the phase space fulfills the continuity equation. But at this point, we remember that in a more abstract form, we have derived many properties of these operations because we have used a general function that we called sigma, and sigma was any function of the coordinates and time. So this density rho is one of the possible sigmas, okay? So for instance, you remember that the partial derivative plus the divergence is equal to the total derivative with respect to time, okay? You remember one of the calculations that we have performed in the last hour, okay? So if the equation 162 is true, and it is true because it is a continuity equation for a function in which nothing is created or destroyed, then also the next equation, 163, must be true. So in a very general way, we have found that the total derivative of the density in the phase space is 0. This is a theorem that is due to Liouville, so it is called the conservation of density in phase, or also the Liouville theorem, okay? And we can also change the form of it. For instance, you remember that we have demonstrated that the divergence of C dot times a function is equal to C dot scalar product, the gradient of the function. So we can restate the Liouville theorem in a form that is the first one in 164, okay? Or maybe we can use the Poisson parenthesis, okay? So we have the second form. Derivative of rho with respect to time is plus the Poisson parenthesis of rho and h is 0. If you look at this equation, okay, it's quite similar to the time derivative of the expectation value of an operator. Remember, time derivative equal to commutator, okay? So also there is a similarity that is produced by using some formalism instead of some other formalism, okay? You remember that rho is a concentration in the phase space, and the phase space is made of two parts. One is the coordinate space, Q, and the other one is the momentum space, P, okay? So we can perform the two integrations one after the other. So if we look at equation 165, we can start with the integration of rho first over the 1/2, so to speak, of the phase space that is made of the p coordinates. So we obtain some function that is equal to d, and of course it depends only on q and time because the p coordinates have been saturated by the integration. And later on we can perform the second integration. We integrate d over the space coordinates q, and we find the total number m. Okay, so immediately you see that d is the density in the q space, because it is a function such that when we integrate it over the q space, we obtain the total number. Okay, we already met this concept when we used an integration of over the K space to find the concentration of the electrons in the conduction band, you remember, okay? Obviously, we could also perform the two integrations in the opposite order, but this is almost never done, okay? But in principle, we could integrate over Q first to obtain some function Q, and then we proceed, we integrate Q to obtain M, okay? Another issue is that the density in the phase space is such that the integral is equal to m, some number m, okay? Of course, if we divide both sides by m, we obtain something else that is equal to 1. Okay, so we can just change the normalization. And we may define another function that we call p, that is simply defined as the density in the phase space divided by m. M is the integral of the density, okay? Obviously, p is normalized to 1. That is, the integral of p over the phase space is equal to 1, okay? Of course, using rho or using p is equally legitimate, but in order to find more analogies with the quantum case, we shall use the second definition using p, because you remember, typically in quantum mechanics, we normalize the wave function to 1 in order to have the probabilities normalized to 1, okay? So we have a distribution of probability in the phase space, whose meaning is the product of p, that is the quantity in the integral of 168, okay? The product of p times dc is the probability to find a representative of the ensemble inside the elementary volume dc, okay? So using this function, we can also now consider what we call the statistical averages, okay? When we have some quantity, any quantity that is defined over the phase space, okay, we may think of considering the average of this quantity, okay? So this quantity is any dynamical function. It could be energy, momentum, angular momentum, whatever. Let's assume that this quantity is some quantity that we do not specify. We call it capital A. And this quantity depends on the generalized coordinates. Okay, so it depends on C. Okay. So what we can do is averaging this dynamic function over the phase space simply by taking the probability P, we multiply A by this probability, And then we integrate over the phase space. Of course, the result will still depend on time, because if the probability depends on time, so if the density is not stationary, okay, then also the average will depend on time, okay? As before, we shall consider only functions A such that the integral that defines the average converges. A very special case, of course, is this case in which the statistical distribution rho or P, okay, describes an equilibrium condition, okay? So if we want that this distribution describes an equilibrium condition, we must impose that it does not depend on time, okay? So there are several methods to do so, okay? So we shall examine some of them, okay? So the easy case is, of course, if we take an equilibrium distribution that is rho equal to a constant, okay? Of course it is good, but well, the integral does not converge, so it is not so good, but in principle we could consider that, okay? A more general case for the equilibrium distribution is that we take the density rho in the form rho depends on some quantity alpha that in turn depends on all coordinates, but alpha is a constant of motion of the system. That means simply that if alpha is a constant of motion, it does not depend on time. That means that also rho does not depend on time, okay? So assume that we are considering alpha as a constant of motion. We have that the derivative of alpha with respect to t is 0 by hypothesis, because alpha is a constant of motion. It follows that the Poisson parenthesis is also 0. Why? Because the Poisson parenthesis of alpha with respect to Hamiltonian, okay, that is shown in equation 170, because if alpha does not have an explicit dependence on time, okay, assume that this is repeated for alpha, okay? So if alpha does not depend on time, this derivative is 0, okay? So it follows that this Poisson parenthesis is also 0, okay? Okay, this is good for alpha, but now we need rho. What happens to rho? How does this property of alpha reflect into a property of rho? Well, very simply, if you consider that rho is a function of alpha, when you calculate the Poisson parenthesis, okay, in order to of rho with respect to the Hamiltonian, if you take the derivative of rho with respect to the coordinates, then you have to take the derivative of rho with respect to alpha, and then you multiply by the derivative of alpha with respect to the coordinates. So the Poisson parenthesis of rho with h is equal to the derivative of rho with respect to alpha, that is some function, times the Poisson parenthesis of alpha with h, and this is 0. Okay? So also we have demonstrated that the Poisson parenthesis of rho with h is 0. Okay? Now we go back to the general expression. It was 164 here. And you find that if the parenthesis is 0, d rho over dt is also 0. So rho has no explicit dependence on time, okay? So according to the definition, it is an equilibrium density, okay? When we want to consider the quantum case, or when we want to transfer somehow these concepts of analytical mechanics to the quantum case, we have a problem. And the problem is here, okay? When we define the elementary volume of the gamma space in the classical description, we have products of elementary of differentials of the coordinates like dq1, and then somewhere here there is also dp1. So we have products of differentials of a canonical coordinate times the differential of the conjugate momentum, okay? But this implies that we are able to know at the same time, with an arbitrarily small error, both position and momentum, okay? This is true in classical mechanics, but it is not true in quantum mechanics. You remember, in quantum mechanics, the coordinate and the conjugate momentum become the coordinate and the momentum operator. And the coordinate and the momentum operator do not commute, so the commutator is non-zero. Actually, the commutator is the reduced Planck constant, okay? So since the two operators do not commute, we have the uncertainty relation involving them. That means that it is forbidden to assume that we can know at the same time position and momentum with an arbitrarily large precision, okay? So this description that is based on partitioning the phase space into elementary volumes does not apply to quantum mechanics, okay? We must do something different, okay? And the reasonable thing is that we must repeat the analysis still in the classical situation, but in view of extending the analysis to the quantum situation, we must partition the phase space into finite elements, not into infinitesimal elements, okay? And these finite elements must be such that the uncertainty principle is not violated, okay? How can we do this? Well, very simply. Instead of using elementary volumes, what we do is we take a finite interval, it is visible here, delta Q. And we subdivide each coordinate axes into equal finite elements delta Q. Then we do the same with each of the momentum axes. We divide them by using finite intervals delta P, all equal to each other. How do we select delta Q and delta P such that the product is the Planck constant? Okay, so in principle we should do 1/2 H bar because it's the minimum, okay, prescribed by the Heisenberg principle. But this is just the same, okay? We simply impose that this product is of the order of H bar, okay? So we are not violating anymore the Heisenberg principle, okay? And so we have subdivided the space, the phase space, into finite elements, okay? This division is also called tessellation. It's a tessellation. It's like putting tiles on the space, finite blocks, okay? This has another consequence that the cells of the phase space are not infinitesimal anymore. They are finite, okay? So they are countable. So instead of using integrals, we must use sums when we repeat the analysis using this strategy, okay? Of course, we are in a multi-dimensional situation because we have the number of axes of the Q-type is equal to S. And the number of axes of the P-type is also equal to S, okay? So each individual product is equal to H, but then we have S times this product. So the actual volume of the cells of the gamma space is equal to the Planck constant to the power S. Okay, so this is the volume of the non-elementary of the small cells of the gamma space, okay? And since these cells are countable, then we indicate the vector C that corresponds to the center of each cell with an index. So the vectors, instead of being called C, that used to be a continuous quantity, they will be called C1, C2, etc. And C1 goes from the origin to the center of the cell number 1, C2 the same, and so on and so on. So the density will also be given an index. So rho E is the density of cell of index E at time t, okay? Then the number of representative points that belong to the cell of index E at time t is some number ME of t that is equal to the product of this density rho E times the volume of the cell, that is times A to the S power, okay? The number of cells is still infinite, okay, because the phase space is infinite, okay? So the number of possible indices is also infinite, okay? So the total number of representative elements will be the sum over all cells from 1 to infinity of the population of the individual cell. And this is obviously equal to the volume of the cell times this quantity. Okay, this is the expression that replaces the integral over the phase space in the continuous case. In the same way, we can define the probability, because the probability is simply the ratio between the probability associated at time t to the cell number E is just the ratio between the population ME of the cell divided by the total population M, okay? And of course, by construction, this probability is between 0 and 1, okay? And of course, the probability fulfills the normalization condition. So the sum over all indices of the probabilities must be equal to 1, okay? Now we can repeat the analysis of the statistical average using the sum instead of the integral. So again, we consider any dynamic function A sub E that is associated with the cell of index E of the phase space. We consider the average of this quantity A as the sum of the values of E over each cell multiplied by the probability at the same instant of time. This is by construction the average, and this definition replaces the integral that was used in the continuous case. Now we introduce a concept that is very important, and this is the concept of entropy. Very likely you are accustomed to consider entropy as a thermodynamic function that is related to temperature and heat, okay? And is one of the possible thermodynamic functions. So you probably know already a macroscopic definition of entropy. But there is also a microscopic definition of entropy, and this microscopic is much more general. Besides, in general, the thermodynamic quantities are considered either in the equilibrium condition or in a near equilibrium condition. In contrast, when you do statistical mechanics, so when you start from the microscopic point of view, there is no need of considering equilibrium. You consider just any situation, okay? So the definition, the microscopic definition of entropy is as follows. Among the possible dynamic functions of which you want to take the average, okay, you may consider the average of log P. So instead of A, that is a general function that is left unspecified for the moment, you consider log of the probability P. So if you look at equation 177, the sum over the phase space of P times log P is by construction or by definition the statistical average of log P. This quantity is not the entropy yet, okay? This quantity is called the Boltzmann H function. So it is called H sub B. It is the Boltzmann H function. Of course, it's a pure number, okay? by construction. And you can see immediately that it is non-positive. Why? Because you remember that the probability P is some number between 0 and 1. Okay, so assume that P is smaller than 1, but not 0. Okay, it's just some strictly smaller than 1 and strictly larger than 0. Okay, so of course, in the sum, you have the product of P that is positive by assumption, and log P that is negative because it is a log of a quantity that is smaller than 1. So for all values that are strictly larger than 0 and strictly smaller than 1, this quantity is negative. Then if P is exactly equal to 1, then the log is 0. And it is multiplied by 1. Okay? So in that case, the result is strictly 0. And finally, if P tends to 0, then the log tends to minus infinity, but it is multiplied by something that is P that goes to 0. And you remember, P is stronger than log P. So P wins. And P goes to 0. So again, in this case, if P goes to 0, then again, the product is equal to 0, okay? If you remember the meaning of P is a probability, okay? So clearly, this probability can never be identically equal to 0 over the phase space, because the points of this phase space must be somewhere, okay? So it is impossible that the population of all cells is 0, okay? Some cells may have a 0 population if they are not reached by any point. These points move in time. They may not be able to reach some points far away in the phase space. So some cells may have a 0 population, okay? Can a cell have a population equal to 1? Well, yes, in only one situation, if all points are in the same cell, okay, because of the definition of probability. If P is 1 in a cell, that means that all points are in that cell and they are not in any other cell, okay? In any case, this HB function is a function that is non-positive. The entropy of the system is defined as the product of the Boltzmann H function times minus the Boltzmann constant Kb. Okay, so the entropy is a non-negative function. It is either 0 or positive. Okay, and the units of the entropy are those of the Boltzmann constant. That is, remember that Kt is an energy, so the units of a Boltzmann constant are Joule over Kelvin. Okay, so these are the units of the entropy. Now, you probably remember that if you take a thermodynamic system, okay, in any initial situation, that means not in an equilibrium situation, okay, in any situation different from equilibrium, okay? And then you let the system go. That means that you eliminate the external perturbations on the system. So you have a box with a gas, and the gas is in any situation that is different from equilibrium, and you just don't touch it anymore, you just wait, okay? You know that eventually it will reach equilibrium, okay? This is some thermodynamic principle that comes from observation. The question is, can we demonstrate mathematically this property? Assume that we can do it. Well, the only thing that we can do is considering the definition 177 of entropy, okay? We must take a system at some initial condition, and then we must calculate how entropy evolves in time. And this is something that we can actually do. It gives rise to a theorem that is called the Boltzmann-H theorem, okay? We can do using the H function because the H function is proportional to entropy. So I just have to change the page because it is somewhere else. Okay, I hope you now are able to see the page. Equation 643 that you see in this page is just exactly the same definition of entropy as before. The only thing that has changed is that the index of the cells, instead of being called E, is called R, okay? So we now want to calculate the time evolution of entropy, and in order to do so, we can just take the derivative of entropy with respect to time, and we see what happens. And this is very easy because we have the time derivative of a product. So we have that the time derivative is equal to p times the time derivative of log, that is 1 over p, so this is where you get the 1, times the derivative of p with respect to time. And then you have log times the derivative of p with respect to 1. So the derivative of the h function is the one that is indicated here as 644, okay? Now, we have just changed the problem, okay? We now have to understand what the evolution of P with respect to time is. So we must understand how the probability evolves in time in order to find the derivative of the probability with respect to time, okay? But this is a relatively easy task because the probability to find a member of the ensemble in one cell changes with time simply because we may have that during the time evolution of the system, some points move from other cells into the cell number R. So if that happens, if they move from outside to the inside of cell number R, they increase the population of the cell. But at the same time, it may happen that inside the cell R, there are particles that move out. In that case, we have a decrease of the population due to this movement of members of the ensemble from the cell to the outside of the cell, okay? So we may state that the number of these transitions must be proportional to the number of members that are present in the cell. For instance, if at time t in the cell of index R there are n members, and if each member has the same probability of changing the cell, the number of members that actually do change cell must be proportional to the number of members that were initially present in the cell. If there are many, there will be many that change. If there is no element in the cell, there is no possibility to change because there is nothing to start with, okay? So we base this on this analysis, okay? We introduce the probability that we call WSR. It is a non-negative number, okay? WSR is the probability that this is called a particle, but it's like a member of the ensemble, okay? In short, we call it the particle. The probability that the particle makes a transition from the cell number S, that is first, to the cell number R per unit time, okay? We assume that we are able to calculate this probability somehow, okay? If we can calculate this probability, then the number of the transitions, of the actual transitions from the cell of index S to the cell of index R per unit time will be the product of WSR times the population of NS. Okay, so this is the contribution from some cell of index S to the cell of index R into which we are interested, okay? Of course, it is a contribution that increases the population of cell of index R. So if we add up over S, we find the contribution of the incoming particles into cell number R, okay? At the same time, we must consider also particles that will abandon cell R, and they will be given by the product of the probability WRS. You see that the indices are inverted because we start from cell R and we end up in cell S, okay, times the population of NR. In conclusion, the variation with respect to time, not of the probability, but of the population, is equal to the total of the positive contribution. This is the first sum is the incoming particles, less the contribution of the outgoing particles, okay? This is the sum of WSR times NS. This is the sum of WRS times RL, okay? You may think that when we sum over all indices, we also sum over the same index R, okay? So we should consider WRR here and there, okay? But they all obviously they cancel each other. So the contributions to the sum in which the indices are equal are irrelevant because they cancel each other, okay? Unfortunately, it is very late, but this is a very interesting calculation, so we shall continue it on Tuesday, okay? The issue is we shall transform the populations into probability in order eventually to be able, going back to this equation, to calculate the evolution of the Boltzmann H function. Okay, so for the moment we stop. I remind you that in the second hour of Tuesday, there will be the distribution of the form for the evaluation of the class, and this will obviously be done electronically, okay, in remote. Thank you very much.